Good evening, and welcome to my festive dining room table. Um, Today, we're going to look at the same ideas that we have involved with forces and Newton's laws, but in kind of a more complex or interesting case where we're not on a level surface anymore, or we have one of the forces kind of tilted at an angle. So the same stuff kind of works, but we need to find components of the forces because they act kind of in different directions. So we need to align all the forces with our kind of two coordinate axis, this x-axis and this y-axis. So this is a little primer on how to do that. So the force of gravity is really like our only constant when it comes to forces. Gravity, the force of gravity will always pull objects downward towards the center of the earth. So that is a force that will always be drawn the same way. But other forces can really vary dramatically. I think in one of the classes we talked about like holding a book against a wall, and that's another case that I didn't even think of besides these three cases. So in the case of holding the book against the wall, gravity still points down, but the normal force, I guess that's also still kind of the same, perpendicular to the surface. So that one is pretty much constant, perpendicular to the surface. But the force of friction was kind of in a weird direction upward because friction opposes motion. So if it was falling down, friction is going to point up. If we have somebody like on a sled, these are one of my more favorite examples, and they're being pulled on the sled, then the force that's applied here, which we might call FA or just F, is no longer just in the x direction. It has some angular component to it. And if it was on a surface that had friction would always also oppose the motion, but notice how now our applied force and our frictional force are no longer in the same direction. So I'll zoom in real big on here. What we have to end up then doing with this force that we have at an angle is finding the components, just like we did. So if we call this force, F, in order to find the component that's balanced with the frictional force, if this was moving at a constant velocity, you need to find the x component of that frictional force. And just like in the previous case, where we could say A being any vector is that vector times cosine theta, we can do that here. Just in our case, the vector is a force. So Fx just equals F, whatever the hypotenuse is, cosine of theta that's given. The same goes for the y component. So some amount of this force is balanced by the force of gravity in addition to the normal force. So there's some amount of the force in this upward or y direction that we can find the component to really easily, just like we did before with this formula on the reference tables, AY equals A sine theta. So Fy is just F. So this is really the same stuff, but just allowing us to stretch our abilities to problem solve with more, realistic or complicated scenarios like the real world is full of. So like sliding or sledding down a hill would be another scenario, which is a little different from our being pulled at an angle or being pulled. And it's different because when we have a hill, we have like an incline here. And if our person, let's say, is sledding down the hill, their force of gravity is still straight down. But the frictional force acts up the hill and the normal force is still perpendicular. So we need to do something here so we can get our forces kind of lined up. So we can use F naught equals ma to analyze the problem. And this is only true if you think about, the direction of acceleration and the ways the forces affect the direction of acceleration. So we'll need to think of interesting ways to change that. So, sorry, my pen died there. So this is, whatever direction the acceleration is in, we want to align the forces so that we are interested, so we can analyze the forces that cause that acceleration. So other scenarios that are a little less common is like when we think about the combined effect of air resistance and gravity on objects flying through the air. So if gravity pulls an object downward, but air resistance kind of pushes it like this, how do we resolve the net force here? So the main types of problems that I'm going to discuss today are these sliding down a hill problems. They're a little trickier than we've seen. So if we consider a simple case of a mass at rest, so it's no longer sliding, and we draw all the forces that act on that. So we have Fg straight down. We have the normal force perpendicular to the surface. And if it's at rest, some amount of this gravitational force is going to pull it down. So there needs to be some amount of frictional force causing it to not move. So we have this kind of issue here where the normal force, so there's theta, the normal force and the frictional force make this nice 90-degree angle. And the force of gravity is kind of like off in its own weird way. And it can help us see that if we rotate the free body diagram so that the normal force is upright, like we're used to seeing. The frictional force is perpendicular to that. But the force of gravity is no longer down. It has this other direction that it's going in because of the angle theta here. So Fg is this oddball. It's off in its own direction. But it can join the other forces on the, if we wanted to call this like the y and x axes, if we break it into components. But we need to figure out where this angle theta shows up in this diagram here. And I'm going to prove to you that that angle theta is actually this angle. So eventually we're going to need this part of the force of gravity and this part of the force of gravity. And this would be this, what we're calling x is parallel to the surface. And what we're calling y is really perpendicular to the surface, or normal to the surface. So sometimes I will call this, actually most of the time I will call this component the component of the weight that's perpendicular to the surface. So it's Fg perpendicular. That's our nice mathematical symbol for perpendicular. And this is Fg parallel. So it's the component of the force of gravity that is parallel to the surface. So if you're not interested in me proving that, you can pause the video here and skip ahead. But basically, I'm just going to redraw this really big and make the box really small. So if we have a big inclined plane and a tiny box, we have the normal force, we have the force of gravity, and we have the frictional force. And we know that this angle theta is the angle theta here. So we're interested in FG perpendicular, which is this component perpendicular to the surface, and FG parallel, which is that component. So ultimately, this is a proof involving trigonometry. So this angle here is a 90-degree angle. And this angle here is a 90-degree angle. So you can think about this in two different ways, but basically if this is theta and this is 90, then this angle right here is theta minus 90, or 90 minus theta rather. So if this right here is 90 minus theta, then this has to be theta. So that's the quickest proof I got for you. The second one is like, these are parallel lines here, and we have two parallel lines cut by a transversal. No, that doesn't work.